Apple juice production in a factory starts the moment large shipments of freshly harvested apples arrive at the intake area, usually packed in massive crates or bins and unloaded using hydraulic tippers. These bins are emptied into stainless steel flumes filled with cool water, which not only begins the cleaning process, but also allows the apples to float gently through the first stages of sorting, protecting the fruit from bruising during transport within the facility. As the apples flow forward, debris such as leaves, twigs, and stones sink and are swept away by underwater conveyors, while the fruit continues toward a mechanical washer that begins the first rigorous stage of surface cleaning. This washer is a rotating, cylindrical drum lined with flexible food-grade brushes and multiple rows of spray nozzles. As the apples spin inside, high-pressure jets of filtered water remove stubborn soil while the brushes scrub the skin evenly without damaging it. This continuous rotation ensures that every surface of each apple is exposed to water and mechanical contact. Exiting the washer, the apples are carried by vibrating dewatering conveyors, which shake off excess moisture and direct the fruit to the optical sorting line. Here, the apples are spaced evenly using mechanical aligners and pass through a tunnel equipped with multi-angle cameras, hyperspectral sensors, and infrared lasers. These technologies analyze surface color, size, shape, and even internal density, allowing the system to detect defects like bruising, rot, or underripeness. Any apple failing the programmed quality thresholds is automatically diverted via precision air jets to a separate path, while the rest proceed to the crushing station. The qualified apples move onto a conveyor that delivers them into a hammer mill or blade grater, which tears them apart into a coarse pulp known as pomace. This mash is made of juice, flesh, skin, seeds, and stems, and is held temporarily in an agitated holding tank to ensure uniformity. The mash is then pumped to a pressing system, often a belt press or pneumatic bladder press. In the belt press method, the mash is sandwiched between two porous synthetic belts that travel between a series of rollers. These rollers gradually increase in pressure, squeezing the juice out of the mash through the belts, while the dry pulp, now significantly reduced in moisture, is scraped off and collected for animal feed or compost. The freshly pressed juice flows into a stainless steel catchment pan and is pumped immediately to a clarification system. At this stage, the liquid is cloudy and filled with suspended solids, primarily made of pectin, starch, and fine plant cells. To remove these, the juice is first treated with a pectolytic enzyme in a stirred tank, breaking down the pectin structure that holds the solids in suspension. After a short incubation period, the juice is pumped into a centrifuge. This high-speed rotating drum forces the heavier particles to the outer wall, allowing the clarified juice to collect in the center. Separated solids are removed continuously from the edge and sent to waste collection tanks, while the juice is directed toward a fine filtration system. In the filtration phase, the juice is passed through multi-stage filters, often plate and frame or cross-flow membrane units that remove particles down to the micron level. The result is a clear, amber gold juice that retains its flavor and brightness while improving shelf stability. From here, the clarified juice is moved to a pasteurization unit via sanitary-grade stainless steel piping. Inline refractometers measure the Brix level of the juice, which indicates the concentration of natural sugars, ensuring each batch falls within the desired sweetness range. Pasteurization is then carried out by pumping the juice through a tubular or plate heat exchanger, where it is rapidly heated to approximately 88 to 90 degrees Celsius for about 30 seconds. This quick, high-temperature exposure inactivates enzymes and destroys any remaining microbial life without altering the flavor or nutritional profile of the juice. Following pasteurization, the juice is flash-cooled using a regenerative system in which outgoing cold juice pre-cools the incoming hot juice, reducing energy consumption while preparing the product for storage. The cooled juice flows into large, sealed, chilled holding tanks with internal paddles that slowly rotate to keep the contents uniformly mixed. These tanks are fitted with oxygen sensors and nitrogen purge systems to minimize oxidation, preserving color and taste. The juice remains here temporarily before either going directly to packaging or being routed through a concentration line. For juice products made from concentrate, a portion of the pasteurized juice is sent to a vacuum evaporator. This multi-effect evaporator reduces the juice under low pressure conditions, allowing water to be removed at relatively low temperatures and preventing thermal degradation. The juice becomes a thick syrup with 1/5 or even 1/6 of the original volume, rich in flavor and sugars. This concentrate is chilled and stored in sealed containers or frozen in large drums until needed. To reconstitute, purified water is added back in precise ratios using inline blending systems, guided by sensors that measure Brix, acidity, and flavor markers. Throughout the process, volatile aroma compounds that were lost during pressing and pasteurization are captured in a flavor recovery unit. This system condenses steam and vapor released during juice handling and separates the desirable aromatic fractions. These recovered flavors are later added back to the juice in the dosing stage to restore the authentic apple profile that might have been muted by heat treatment. The flavor dosing step is conducted just before packaging, ensuring that the final product retains its freshness and natural character. The next step is deaeration. The juice, whether from concentrate or fresh pressed, is transferred to a vacuum chamber where dissolved oxygen is removed. Oxygen in the juice can lead to discoloration and off flavors over time, so the vacuum deaerator reduces this risk while extending shelf life. Following this, the juice is passed through a final sterile filtration system that ensures it is free of any remaining particulates or microbial contaminants. Now fully processed, the juice proceeds to the filling line. Here, sterilized bottles or cartons are fed into a sterile chamber, often using an airlock or overpressure system with HEPA filtered air to prevent airborne contamination. The juice is filled into containers using gravity fillers or pressurized nozzles that match the flow rate to the container size. Fill levels are monitored in real time by sensors and load cells, and any underfilled or overfilled containers are rejected automatically. Immediately after filling, each bottle is capped and sealed. Caps may be steam vacuum sealed or induction sealed depending on the packaging format. The seal ensures tamper resistance and microbial safety. Bottles then pass through a cooling tunnel or water spray cascade to bring the product temperature to storage levels. A high-speed labeler applies branded labels, while laser printers mark each bottle with a production date, expiration date, and batch identification code. These codes are linked to the factory's ERP system, allowing every bottle to be traced back to the exact origin and processing conditions of the apples used. Once labeled, the bottles are grouped into multi-packs or trays, shrink-wrapped, and placed onto pallets. Robotic palletizers stack the cases according to programmed patterns optimized for stability and transport efficiency. Each pallet is wrapped in stretch film, labeled with its batch data, and assigned a position in the cold storage warehouse. Inside the warehouse, temperature is carefully maintained and monitored, and inventory is managed with barcode scanning and automated tracking systems. When orders are placed, pallets are retrieved, scanned, and loaded onto refrigerated trucks using guided forklifts or automated shuttles. Mango juice production in a factory begins with the unloading of ripe mangoes delivered in large crates or bins that can weigh several hundred kilograms each. These bins are emptied into a receiving chute where the mangoes are guided into a flotation tank. This tank is filled with clean water, allowing the mangoes to float and separate naturally from heavier debris like stones, dirt clumps, or leaves. The floating system helps prevent bruising while also initiating the cleaning process. Submerged conveyor belts or rotating paddles gently propel the mangoes through the tank. From there, the fruit is lifted by inclined belts and directed toward a high-capacity washing machine. The washing machine consists of rotating, soft-bristled brushes and high-pressure water jets arranged in multiple stages. These brushes scrub the mango skins, while the jets remove dirt, surface residues, and any traces of pesticide. The rotation and brushing ensure that every mango is cleaned thoroughly on all sides without causing damage to the fruit's flesh. After this stage, the mangoes pass through a rinsing tunnel where filtered water gives them a final clean before they're ready for sorting. Once cleaned, the mangoes travel along a vibrating dewatering belt that removes residual water, then onto a grading and sorting line. Optical sorting systems equipped with multispectral imaging cameras analyze each fruit's size, shape, and color. Defective fruits showing signs of rot, underripeness, or physical deformities are automatically ejected using targeted air jets. The remaining mangoes, now considered processing grade, are transferred to the peeling and destining area. Unlike apples or oranges, mangoes require more complex handling due to their fibrous flesh and large central seed. The mangoes first pass through an inspection belt, where their orientation is corrected for proper alignment. They then enter a peeling machine equipped with abrasive rollers or sharp rotating blades that remove the outer skin. In some configurations, steam peeling may be used, where the mangoes are exposed to high-pressure steam for a few seconds, causing the skin to loosen and making it easier to remove with rubber rollers. After peeling, the mangoes are fed into a destining unit. This destining system is designed specifically to handle mangoes. As the fruit enters, it is squeezed against a grating or sieve by rollers that force the pulp and juice out through the mesh, leaving the large stone behind. These stones are ejected and collected for disposal or further processing in separate streams. The extracted pulp, still containing fibrous strands and varying in consistency, is collected in stainless steel tanks equipped with gentle agitators that keep the mixture homogeneous. At this point, the mango pulp is thick and viscous with varying amounts of fiber depending on the mango variety. To refine the texture, the pulp is sent through a pulping and refining line. First, it enters a pulper equipped with rotating blades that shear the pulp and reduce the fiber size. It then passes through a finisher or decanter centrifuge that separates out any remaining coarse fiber, unbroken skin fragments, or seed residues. The resulting puree is smooth, thick, and uniformly textured, ideal for juice production. This puree is stored in chilled, sealed holding tanks to await further processing. Next comes the standardization phase. Mango juice requires specific sweetness and acidity levels to maintain product consistency, especially when fruit quality and ripeness vary. The puree is transferred into blending tanks, where it is analyzed for Brix, sugar content, pH, and viscosity using inline sensors and laboratory instruments. Based on this analysis, adjustments are made by adding water, sugar syrup, citric acid, or fruit concentrates. If the product is to be marketed as nectar or a mango beverage rather than pure juice, the ratio of mango content to added water is adjusted accordingly. Throughout this blending stage, high shear mixers are used to ensure all components are thoroughly and evenly incorporated. With the base juice now standardized, it moves on to pasteurization. The juice is pumped through a heat exchanger where it is rapidly heated to between 85 and 95 degrees Celsius for a precise duration, typically around 30 seconds, to deactivate enzymes and eliminate any microbial contaminants. The pasteurization temperature and time are tightly controlled, using automated sensors that adjust flow speed and heating elements based on real-time data. After heating, the juice is flash-cooled using a counterflow plate exchanger, bringing it down to bottling temperature, typically just a few degrees above ambient. Before packaging, the juice may undergo deaeration. Mango juice, due to its thickness and high natural sugar content, is prone to oxidation, which can alter color and flavor. In a vacuum deaeration chamber, the juice is exposed to low pressure, causing dissolved oxygen and other gases to be removed. This protects the flavor and extends shelf life. For products labeled as with mango aroma or for high-end juice lines, a flavor recovery system is also employed. During pasteurization and pulping, volatile aroma compounds are captured from the evaporated vapors, condensed, and stored in small tanks. These aromas are then reintroduced into the juice at controlled concentrations to restore the characteristic fruity bouquet. At this stage, the mango juice is fully prepared and ready to be packaged. The packaging hall is a high hygiene zone with controlled air filtration, often operating under positive pressure to keep contaminants out. Empty bottles or cartons are first sterilized using ultraviolet light, steam, or hydrogen peroxide mist. These containers move into a filling carousel where the juice is dispensed into each unit using volumetric or gravity fillers. Sensors ensure that each container is filled to the exact target level, and any discrepancies are immediately rejected by the control system. After filling, bottles are capped or sealed and sent through a cap sterilization tunnel to eliminate any surface bacteria introduced during capping. Each sealed unit is then passed through a coding station where laser or inkjet printers mark the label or neck with production dates, expiry dates, and batch numbers. The bottles are labeled using high-speed machines, which apply adhesive or shrink-wrap labels depending on the format. A visual scanner confirms that every container is correctly labeled and marked. Any mislabeled bottles are rejected into a separate collection chute for reprocessing. Once labeled, the bottles are grouped into packs, shrink-wrapped, and moved to an automated palletizing system. Robotic arms arrange the bottles into patterns on wooden or plastic pallets, optimizing for stability during storage and shipping. Each pallet is then wrapped with stretch film, weighed, and tagged with a tracking barcode. These barcodes are linked to a centralized inventory system that records every detail of the product's production, packaging, and quality control data. This enables full traceability from the factory to the retailer. Before shipping, the pallets are stored in temperature-controlled warehouses. Mango juice, especially when not preserved with artificial additives, is sensitive to heat and light, so storage areas are kept cool and protected from UV exposure. During storage, samples from each batch are periodically tested for microbiological stability, pH drift, sugar degradation, and visual clarity. These checks ensure that the product maintains its intended quality over time. Any deviation prompts an investigation and can trigger a hold on the affected batch. Finally, when orders are placed, the pallets are scanned, retrieved by automated guided vehicles or forklifts, and loaded into refrigerated trucks. Logistics systems plan delivery routes and timing to maintain cold chain integrity, ensuring the mango juice reaches distribution centers, supermarkets, or export terminals without temperature fluctuation. Throughout this entire process, factory systems continuously log data, temperatures, flow rates, batch compositions, and equipment performance to ensure complete quality assurance and compliance with regulatory standards. In the high output production of Coca-Cola, the process is defined by continuous motion, absolute precision, and the seamless choreography of ingredients, machines, and packaging systems that transform individual raw components into millions of finished beverages every single day. The process begins deep within the mixing facility, where highly purified water, stripped of all minerals, chemicals, and organic material through a series of activated carbon filters, deionization beds, and ultraviolet treatment chambers, forms the foundation of the beverage. This purified water, tested continuously for pH, conductivity, and microbial presence, is stored in stainless steel tanks where it awaits dosing. Simultaneously, concentrated syrup, pre-mixed to exact proportions in controlled rooms, is pumped from insulated holding tanks through jacketed pipelines that maintain a constant temperature to prevent any crystallization or viscosity shifts. These lines carry the syrup to the blending system, where the water and concentrate meet inside high-speed mixing chambers fitted with vortex turbines that spin at thousands of revolutions per minute. These turbines ensure that every drop of syrup disperses evenly throughout the water stream, achieving uniform flavor concentration at massive scale. Inline refractometers measure sugar content and density in real time, adjusting flow valves to keep the bricks level within fractions of a percent of specification. Once blended, the now recognizable but uncarbonated Coca-Cola base enters a chilling loop, where it is passed through plate heat exchangers that rapidly drop the temperature to just above freezing. This cooling is critical because carbonation requires both precision and cold liquid. Warmer temperatures reduce the solubility of carbon dioxide, and the beverage must be stabilized before the gas is introduced. The chilled liquid is then sent to the carbonation unit, a sealed pressurized chamber where CO2 is injected under precise pressure and temperature control. The carbon dioxide gas, stored in liquid form in cryogenic tanks, is vaporized and filtered before injection, ensuring purity and taste neutrality. As the CO2 is forced into the beverage under pressure, it dissolves instantly, and the resulting mixture, now fully carbonated Coca-Cola, is routed into buffer tanks, where it is gently agitated to maintain consistency and avoid foaming. These tanks are under positive pressure to prevent degassing, and every line is monitored for CO2 saturation, temperature drift, and fill levels. From these tanks, the carbonated beverage moves directly to the filling lines, which operate with unbroken efficiency, handling thousands of bottles or cans per hour with mechanical repetition and minimal tolerance for variation. For bottles, the first step begins with preforms, small plastic tubes made of PET, fed from hoppers into a rotary oven where they are heated to a malleable state, then transferred into a blow molding carousel. Inside this machine, each preform is stretched and inflated with high-pressure air into the shape of a bottle inside precision-machined metal molds. The formed bottles are immediately cooled, trimmed, and transferred onto conveyors that carry them upright toward the filling line. Throughout this path, they remain untouched by hands and isolated from ambient air by enclosed systems that maintain sanitary conditions. As they approach the filler, the bottles are inverted and rinsed internally with sterile air or ionized water to remove any particles. They then pass under the filling heads, nozzles that lower into the neck of each bottle, creating a tight seal and filling them under counter-pressure conditions to prevent foaming or CO2 loss. The entire filling cycle for each bottle takes only a few seconds, monitored by laser-level sensors that detect exact volume. As each bottle fills, the flow is throttled to avoid turbulence, and the gas pressure is equalized to maintain carbonation stability. Immediately after filling, the bottles are transferred to the capping station, where precision-guided turrets place caps onto each one and tighten them with calibrated torque drivers. The caps themselves are fed from vibratory bowls that align them correctly and move them through high-speed chutes. As each bottle is capped, it is passed through a vacuum checker that detects seal integrity by measuring internal pressure, and any container that doesn't meet the threshold is automatically diverted from the line. In parallel to bottle filling, production follows a similarly synchronized path. Aluminum cans arrive already formed, stacked, and nested and are depalletized in towers that feed them one by one onto high-speed conveyor belts. These cans move through a rinse tunnel where jets of deionized water clean the interiors. Then dry blowers remove every drop before they reach the filler. Because cans can't be sealed under counter pressure like bottles, they are filled with a slightly different method. First purged with carbon dioxide to displace oxygen, then rapidly filled with cold, carbonated Coca-Cola, and finally topped with lids while still under pressurized gas. The lid seamer seals each can by curling the edge of the aluminum lid around the lip of the can body and compressing it tightly with a roller under immense force. The seam is inspected by cameras and load sensors, and every few hundred units, samples are removed automatically and sent to inline X-ray or cutaway analysis to ensure structural integrity. Once sealed, the cans are dried again, passed through a date coder that prints production codes and batch identifiers directly onto the lid, and then sorted into lanes based on packaging format: single, multi-pack, or bulk tray. Now fully sealed, bottles and cans alike move toward labeling and secondary packaging. Bottles pass through shrink sleeve or wraparound labelers that align each container using optical sensors before a printed film sleeve is applied and shrunk into place using steam or infrared tunnels. Can multi-packs are grouped into clusters by mechanical pusher arms and wrapped in printed film or placed into cardboard carriers. Robotic arms lift and arrange finished units into cartons or trays, depending on regional packaging standards, and automated check weighers confirm product count and configuration within each package. After secondary packaging, the products move to palletizing stations. Here, robotic stackers use vacuum grippers or clamp heads to build pallets layer by layer, rotating and interlocking packs to maintain balance and optimize density. Slip sheets or corner boards may be inserted for additional stability. Once complete, each pallet enters a rotary stretch wrapper, where clear plastic film is wrapped under tension around the stack, binding it tightly to protect against vibration or shifting during transport. A thermal label is printed and applied to the outer film, displaying destination, pallet ID, and manufacturing metadata. Every part of the line, from syrup mixing to final wrapping, is connected to a centralized control system, often SCADA-based, which aggregates data from thousands of sensors across the production floor. It tracks real-time flow rates, fill volumes, pressure changes, CO2 consumption, label placement accuracy, packaging efficiency, and quality checkpoints. Alerts are triggered the moment a parameter deviates from its programmed limits, prompting either automatic correction by servo-driven actuators or shutdown protocols to isolate the issue for inspection. Quality assurance is deeply embedded into the process. Sample bottles and cans are pulled at regular intervals by robotic pickers and sent to adjacent quality labs, where automated instruments test for bricks levels, carbonation volume, pH, color density, and turbidity. Gas chromatographs may analyze flavor profile consistency, and oxygen analyzers confirm shelf life integrity. Retention samples are archived from each production batch in cold storage, enabling full traceability in case of future inquiry. Cleaning in place systems activate between flavor runs or at set intervals, flushing pipes, tanks, and filling valves with heated caustic solutions, followed by acid rinses, and finally with purified water. All internal product contact surfaces are sanitized, and the data logs are updated with each wash cycle. This ensures the system is sterile before the next production batch begins, whether it's more Coca-Cola or a different product line altogether. All along the line, mechanical timing is critical. Bottles that arrive milliseconds too soon or too late can cause backup or collision, so every machine is programmed to respond to product flow, spacing, and acceleration. Timing screws, sensors, and motorized star wheels maintain precise positioning, And buffer conveyors absorb temporary surges without stopping the line. Overhead, cameras and inline vision systems inspect every package for branding alignment, color accuracy, seal integrity, and tamper evidence, discarding any product that fails visual QA. From a distance, the system appears to operate like a single, unified machine. Syrup, water, gas, packaging, and automation all working as one organism, never pausing, never deviating. Every bottle and every can moves through this stream of equipment with exacting control, shaped not by hand, but by air pressure, centrifugal force, liquid dynamics, and heat energy, and by the software that orchestrates it all behind the scenes. The production of cherry Coca-Cola begins with the coordinated movement of ingredients through a tightly integrated system of tanks, pipes, mixers, fillers, and control panels, where every second of the process is timed, and every variation in flow, pressure, or temperature is monitored and corrected in real time. The defining element of this beverage, the distinct cherry-flavored profile, requires its own set of ingredients to be introduced at specific intervals within a continuous fluid stream, and the entire operation is driven by automation that ensures each bottle or can delivers the same flavor, carbonation, and experience without deviation. At the heart of the operation lies the mixing zone, a sealed chambered area of the factory where the formulation begins not with bottles or packaging, but with the controlled blending of ultra-purified water and concentrated syrup. The water itself is subjected to a multi-stage filtration process that removes every mineral and contaminant through reverse osmosis membranes, UV sterilization lights, activated carbon beds, and deionization columns. The final water output is chemically neutral, consistent in temperature, and free of flavor interference, ensuring it will not alter or dull the delicate cherry infusion that characterizes the product. Simultaneously, the cherry Coca-Cola-based syrup is prepared in mixing tanks where measured amounts of sweeteners, flavor agents, acidity regulators, and natural cherry extracts are combined into a thick, dark syrup with precise viscosity. Each batch is homogenized with high-speed impellers, continuously monitored for density using inline refractometers, and sampled through sterile taps for real-time verification of its sugar content, aroma, and visual clarity. Once verified, the syrup is stored in insulated holding tanks fitted with agitators to prevent settling and ensure uniformity prior to dosing. When the purified water and cherry-infused syrup are combined, they are fed into high-shear blending, chambers where specially engineered turbines swirl the mixture at controlled speeds to ensure total integration. These blending units include flow regulators that adjust the syrup-to-water ratio down to tenths of a percent so that every liter leaving the chamber maintains exact sweetness and acidity levels. This blending is continuous and uninterrupted, forming a central stream of cherry Coca-Cola base that is directed toward the chilling loop. Before carbonation, the mixture is rapidly cooled using a set of plate heat exchangers where cold glycol fluid moves through alternating stainless steel plates, drawing heat from the beverage as it flows in an adjacent channel. The cooling process is essential, dropping the beverage temperature to near freezing, around 0 to 2 degrees Celsius, which allows the carbon dioxide to be absorbed efficiently and held within the liquid under pressure. Once chilled, the drink enters a sealed carbonation unit. Inside this pressurized chamber, carbon dioxide gas, stored in liquid form at cryogenic temperatures, is vaporized, filtered, and then injected into the cold cherry Coca-Cola base through a sparging system that disperses the gas evenly throughout the liquid. The CO2 dissolves into the beverage instantly due to the low temperature and high pressure, and the resulting carbonated drink flows forward to the buffer tanks, where it is gently mixed and held under pressure to prevent gas release or foaming. These buffer tanks act as holding silos between mixing and filling, maintaining consistent temperature and carbonation levels while regulating the supply to each individual filling line. The tanks are fitted with pressure sensors, degassing valves, and agitation paddles that rotate at slow speeds to preserve homogeneity without disturbing the carbonation level. From here, the carbonated cherry Coca-Cola is ready to be dispensed into containers at high speed. If bottles are the intended format, production begins with PET preforms, small test tube-shaped plastics that are loaded into feed trays and passed through a rotating oven chamber fitted with infrared heaters. The preforms are warmed to a pliable temperature before being inserted into steel molds, where compressed air blows each preform into the shape of a bottle within milliseconds. The molds are cooled, and the newly formed bottles are ejected onto conveyor lanes, where they begin their journey to the filling line. Each bottle passes through an inversion unit, where they are turned upside down and rinsed with filtered air or ionized water to eliminate static charge and remove any residual particles. Once cleaned, they are flipped back upright and enter the filling carousel, a large rotating ring with multiple filling heads. As each bottle passes underneath a head, it is sealed airtight and filled using counter-pressure filling. CO2 is first used to purge oxygen from the bottle. Then the beverage is dispensed, equalizing pressure to avoid foaming or gas loss. As the bottle fills, a level sensor determines the precise volume, and flow is shut off with a clean break once the target fill is reached. The next stage is capping. Cap hoppers sort and orient the plastic caps, feeding them down a chute where robotic arms place each cap onto the filled bottle. A torque-controlled spindle tightens every cap to an exact specification, and a vacuum sensor checks that each seal is secure. Each bottle then passes through a high-speed date printer that applies production information, including line number, time code, and expiration date. Can filling follows a similar track, but on a separate line with specialized machinery. Empty aluminum cans arrive pre-formed, palletized, and stacked in tall columns. These stacks are depalletized and fed into the can rinsing tunnel, where they are cleaned with a high-pressure deionized water spray, then dried using high-speed air knives. Cleaned cans are conveyed directly into the filling system, where they pass beneath a gas flush station that replaces internal air with carbon dioxide to maintain freshness. As the cherry Coca-Cola is dispensed into each can, the filling head retracts, and a lid is placed onto the top of the filled can by a precision seamer. This machine uses a dual-action compression and curl technique to lock the lid onto the can body, creating a hermetic seal. Immediately afterward, the can is cleaned again externally, printed with production codes, and passed to the packaging lanes. At this point, both bottles and cans converge into the secondary packaging area, where products are grouped, aligned, and prepared for shipment. Bottles are collected into multi-packs using servo-controlled arms that lift and guide them into shrink film, which is wrapped and sealed around the group before passing through a heat tunnel that shrinks the film tight. Cans are guided into multi-lane collators that align sets of 6, 12, or 24, depending on the package, and apply either shrink wrap or cardboard wraps printed with branding and barcodes. Cameras verify each pack's alignment, color fidelity, and integrity before they are cleared for stacking. Packaged units move toward robotic palletizing systems, where vacuum lifters and grip arms organize them into stable layers, rotating the orientation of each pack to create interlocking rows. Slip sheets are inserted between layers, and once the pallet reaches full height, it is transferred into an automatic stretch wrapper, which encases the pallet with tensioned film from top to bottom. A printed label with barcodes, destination data, and production batch is applied to the outside, and the pallet is transferred to the loading dock for transport. Meanwhile, every single movement on the production floor is tracked by an integrated control system, a network of programmable logic controllers and interface stations that monitor temperature, pressure, syrup ratios, carbonation levels, fill rates, and flow speed. The system adjusts each parameter in real time. If syrup density increases due to ambient temperature, pumps slow fractionally. If bottle alignment drifts off center, the guide rails shift laterally. If carbonation drops even slightly, the gas injector valve pulses at higher frequency until the correct level is restored. Throughout the process, quality assurance teams collect real-time data from sensors and pull physical samples at intervals. These samples are sent to inline labs, where technicians run automated tests using densitometers, CO2 analyzers, pH probes, and colorimeters to ensure each bottle or can meets flavor, appearance, and stability specifications. A taste panel may confirm final flavor consistency before the batch is cleared for release, and a retention sample is archived for traceability. Between batches, the entire system undergoes a clean-in-place (CIP) procedure. Pipes, valves, tanks, and filling heads are flushed with heated alkaline solutions, followed by acidic rinses and sterilization stages. Sensors monitor residue levels in rinse water, and the system will not allow a new batch to begin until cleanliness thresholds are met across the entire line. Inside the production facility dedicated to Coca-Cola Zero, the operation begins with a steady rhythm of systems calibrated to blend, chill, carbonate, and package a product that relies on absolute precision. Because unlike its sugar-sweetened counterparts, Coca-Cola Zero is formulated with no sugar at all, relying instead on an exact balance of non-nutritive sweeteners that must be handled with extraordinary control to maintain both flavor integrity and regulatory compliance. The process begins not with packaging, not even with carbonation, but with water. Water that has been stripped of every mineral, ion, and microbe through a comprehensive purification chain that includes activated carbon filtration, multi-stage reverse osmosis membranes, ultraviolet sterilization, and final stage polishing filters to ensure that every molecule entering the blend tanks is completely neutral. This water, once purified, is cooled immediately and transferred into a network of stainless steel supply tanks, each one connected to high-flow dosing manifolds, where the Coca-Cola Zero concentrate is introduced. Unlike other formulas, the Coca-Cola Zero syrup contains highly sensitive ingredients that must be mixed with close control over both flow rate and agitation speed. A series of variable speed turbines inside a baffled blending chamber begins to stir, drawing in sweetener concentrates from microdosing pumps which meter out fractions of grams per second, ensuring that every liter of finished product will contain only the approved quantity of aspartame, acesulfame potassium, and other formulation components. The syrup is mixed with chilled, purified water in a continuous loop, constantly circulating through inline density sensors and refractometers that verify every measurable characteristic of the mixture: its Brix equivalent, its acidity level, its color profile, and its consistency, all monitored by SCADA systems that relay performance data to centralized control stations positioned throughout the factory floor. If the syrup becomes too concentrated, water flow is increased fractionally. If any temperature drift is detected in the mixing tank, the coolant jacket is adjusted to compensate instantly. The goal is absolute uniformity. Every second, every drop must match the one before it. As the base liquid moves into the carbonation stage, it passes through a final chilling module where its temperature is brought down to a near freezing range. At this point, the beverage is ready for carbonation. The carbon dioxide gas, stored in its own cryogenically cooled system, is injected into the mixture using a high-efficiency carbonator, a pressurized steel chamber where the CO2 enters under regulated pressure through micro-diffusers, creating billions of microscopic bubbles that dissolve immediately into the cold liquid. The flow of CO2 is continuously calibrated according to beverage temperature, system pressure, and product viscosity, with flow sensors and back pressure valves maintaining stability as thousands of liters pass through each hour. Once fully carbonated, the beverage is routed into pressurized holding tanks, buffer vessels that serve as the final point of quality assurance before the product reaches the filler. These tanks are lined with level indicators, gas traps, and temperature probes, all synchronized to maintain the carbonation level while gently agitating the liquid to prevent stratification or foaming. Here, any final testing is performed in line. Carbonation volume, turbidity, residual sweetness, and pH are verified one last time. A sampling valve allows automated collection of product every few minutes, and that sample is passed directly into a micro lab for flavor standardization analysis using spectrophotometry and gas chromatography. Meanwhile, the packaging line is already in motion. For plastic bottles, the process starts with injection molded preforms, small and thick-walled, which are delivered in bulk and stored in hoppers above the blow molding machines. These preforms descend through a heater array where infrared panels warm them to a precise forming temperature before they are dropped into two-part molds. Compressed air is blasted inside, expanding the plastic against the inner mold walls to create full-size bottles instantly. As the mold opens, cooled air is used to solidify the bottle's shape, and a robotic gripper places each new bottle upright onto a moving conveyor that feeds directly toward the filling station. Before any liquid enters the bottles, they are passed through an inverted rinsing tunnel where ionized air is sprayed inside each one to remove microscopic particles. They continue along the line toward the filler, where a rotary system spins each bottle into place beneath a filling valve. This valve descends into the mouth of the bottle, creates a pressurized seal, and initiates a filling sequence that begins with a brief CO2 purge to eliminate oxygen and preserve shelf stability. The pressurized beverage flows into each bottle in just under 2 seconds, with real-time fill level sensors using laser measurement to verify that each container is consistent to the milliliter. There is no overflow, no foam rise, no turbulence. The pressure balancers are engineered to make the fill seamless and silent. Once filled, the bottles pass immediately to the capping turret. High-speed feeders deliver bottle caps from a bowl sorter into the capping head, which presses each cap onto the threads and twists them into place using torque-monitored spindles. Each cap is verified for application tightness and angle, and a vacuum test is performed at random intervals by an inline tester that verifies the seal by measuring pressure drop inside a chamber. If a cap is misapplied, the bottle is instantly diverted from the line. After capping, the bottles pass through a date and batch printer, which uses thermal inkjet or laser etching to apply identification directly to the neck or shoulder of the bottle, depending on line configuration. In parallel, aluminum cans are prepared on their own dedicated track. Delivered by the pallet, preformed cans are depalletized and sent through a high-speed depuck system that guides them into the line one at a time. Each can passes under a rinse sprayer and then through a drying tunnel before entering the can filler. This equipment is built for volume. Multiple nozzles dispense product simultaneously, filling dozens of cans per second, each one pressurized beforehand to prevent foaming during the rapid fill. A lid is placed on each can immediately after filling, and a seam roller presses the lid onto the body, creating a hermetic seal that is pressure tested, scanned by vision systems, and validated against a standard profile. Cans are printed with batch codes and transferred to the packaging section. Now, both bottles and cans proceed to the secondary packaging area, where multi-packs are created using automated grouping systems. Bottles are collated into clusters of 6, 12, or 24, wrapped tightly in shrink film, and sent through a steam tunnel that shrinks the plastic smoothly around the group without obscuring the labels. Cans are similarly grouped and placed into printed cardboard sleeves or plastic rings, depending on the destination. Each group is weighed, scanned, and inspected for alignment before being transferred into cartons. Carton erectors form boxes from flat stock, fold them automatically, and glue them using hot melt adhesives before they are filled with packs by robotic arms that stack them precisely inside. Once loaded, the cartons are sealed, labeled, and conveyed to a palletizing system where mechanical arms stack them onto pallets in programmed patterns to maximize space and stability. A slip sheet may be inserted between layers, and once the stack is complete, it moves into a stretch wrapper that encases the pallet with plastic film to lock it tight for shipping. The entire pallet is weighed, labeled, and scanned before being queued for loading. Orange juice production in a factory begins with the arrival of fresh oranges in massive quantities, typically delivered by trucks carrying bins or crates that can hold thousands of pounds of fruit. The oranges are poured into large hoppers and then guided along a vibrating conveyor system that helps to separate any debris such as leaves, twigs, or clumps of soil. As the fruit moves forward, it passes through an initial rinse system where pressurized water jets spray away surface dirt and residues. Rotating drum washers further agitate the oranges, scrubbing them gently with food-grade brushes to ensure the peels are completely clean before any juice extraction begins. Once washed, the oranges travel up an inclined conveyor that feeds into a mechanical grading line. This line uses a series of rotating rollers with increasing gaps that allow smaller or misshapen oranges to fall through and be separated from the main batch. Optical sorting systems are often installed here as well, using cameras and infrared sensors to inspect the surface quality and color of each orange. Damaged or underripe fruit is ejected automatically by a timed air puff system. Only high-grade oranges make it past this point, continuing along the line toward juice extraction. Next, the sorted fruit enters the sizing stage. Here, the oranges are divided into different lanes based on diameter. This ensures that each juicing unit receives fruit of uniform size, which helps maintain consistent yield and reduces strain on the equipment. The oranges are guided into feed channels that position them directly into the juice extractors. These machines are highly specialized. They operate by slicing the orange in half and then pressing each half against a conical reamer, while simultaneously filtering out seeds and peel fragments. Some systems use a piston and cup configuration, where a whole orange is pressed between a domed upper cup and a lower cutting tube that pierces the peel and squeezes out the juice under high pressure. The extracted juice flows downward into stainless steel collection pans beneath the extractor units. At this point, it still contains pulp, peel oil, and small fibrous fragments. The juice is directed through a coarse mesh screen that removes large solids, then flows into a centrifugal separator. This machine spins the juice at high speed inside a cylindrical drum, using centrifugal force to separate pulp and heavier particles from the liquid phase. The resulting juice is brighter and clearer, but it is still far from ready for bottling. From here, it enters a balance tank that acts as a buffer, feeding the next. Processed continuously even if there's a brief pause upstream. The juice is then pumped toward a heat exchanger for pasteurization. Before entering, the juice is measured for its Brix level, the concentration of dissolved sugars, using inline refractometers. This allows technicians to ensure the juice meets sweetness specifications. As the juice enters the heat exchanger, it flows through a system of narrow stainless steel tubes that are heated externally by hot water or steam. The juice is quickly brought up to a pasteurization temperature, typically around 90 degrees Celsius, for a brief period of time, often under 30 seconds. This short heat burst is enough to kill off any harmful microorganisms or enzymes that could cause spoilage without damaging the fresh taste of the juice. After pasteurization, the juice is rapidly cooled by a regenerative cooling loop where the incoming cold juice cools the outgoing hot juice through thermal exchange. This keeps energy usage efficient while ensuring that the juice exits at a safe and stable temperature, usually just above freezing. The cooled juice is then stored in large, chilled stainless steel holding tanks. These tanks are equipped with slow-moving agitators that keep the juice uniformly mixed and prevent settling. The tanks are sealed and often nitrogen purged to reduce oxidation and preserve flavor during this intermediate stage. Depending on the product being made, this base juice can now follow different paths. For not from concentrate orange juice, the liquid moves almost directly to packaging. For from concentrate production, the juice is sent to an evaporator system. Here, the water is removed by gently heating the juice under vacuum conditions, allowing water to evaporate at a much lower temperature than normal boiling. The result is a thick, syrupy concentrate with only about 1/6 of the original water content. This concentrate is easier and cheaper to store and ship, and later in the process, it will be reconstituted by adding purified water back in to reach the original volume and consistency. Regardless of the juice type, another critical step occurs in parallel: flavor recovery. When juice is extracted and pasteurized, volatile aromatic compounds are released into the vapor phase and lost unless captured. A dedicated flavor recovery unit condenses these vapors and separates out the essential oils and aroma compounds, which are stored in small, sealed vessels. These recovered flavors are later added back into the juice, either before packaging or during the reconstitution stage, to restore the characteristic citrus profile that would otherwise be dulled by processing. In the case of juice with pulp, a controlled amount of pulp is reintroduced into the clarified juice. The pulp is collected from earlier filtration stages, passed through a sterilization step, and dosed into the juice stream in precise proportions. Flow meters and mix tanks ensure that every bottle or carton has uniform pulp content throughout the batch. With the juice now stabilized, flavored, and standardized, it moves to the final filtration and deaeration stage. Fine filtration using microfilters ensures that no residual particulates remain in the juice. Deaeration systems use vacuum chambers to strip out dissolved oxygen from the juice, which helps extend shelf life and reduces oxidation of flavor compounds. The oxygen-free juice is now ready for final packaging. The packaging system begins with bottle or carton sterilization. Empty containers are passed through a sterile air tunnel or sprayed with a sanitizing agent like hydrogen peroxide. They are then rinsed and dried before entering the filling machine. The juice is filled into bottles using positive pressure or gravity fillers in a sterile chamber with HEPA-filtered airflow to prevent microbial contamination. Each bottle is filled to exact specifications, checked by weight sensors or laser volume detectors, and immediately capped with a tamper-evident closure. The sealed bottles proceed through a cap sterilization tunnel and then into a final pasteurization or hot water shower, depending on the product's distribution requirements. After this thermal stabilization, the containers are labeled by high-speed machines that apply shrink sleeves, wraparound labels, or printed adhesive labels depending on format. Inkjet printers mark the production date, expiration date, and batch number on the cap or neck. The bottles are then grouped into trays or shrink-wrapped into multi-packs. These are placed onto pallets in a programmed stacking pattern optimized for load stability and storage efficiency. Robotic arms or palletizers stack the packs, and each pallet is wrapped in stretch film and affixed with a shipping label that includes traceability codes. The pallets are then transferred to refrigerated storage areas where the temperature is tightly maintained to keep the juice fresh before distribution. Every stage of the process is monitored by a centralized control system that collects data from sensors embedded throughout the line. Flow rates, temperature curves, pressure differentials, pH levels, and oxygen content are all tracked in real time. If any measurement drifts outside of specified limits, alarms are triggered and corrective actions are taken to ensure product quality is never compromised. Quality assurance teams collect periodic samples for laboratory testing, checking not only microbial safety, but also taste, color, texture, and chemical composition. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used, where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems, rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey Company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented, dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, all ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based PET alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. The story of Dunkin' Donuts began in 1950 when William Rosenberg opened the first location in Quincy, Massachusetts. His vision was to provide high-quality coffee and donuts quickly and affordably, catering to workers looking for a convenient breakfast. The brand grew rapidly, expanding nationally and then internationally, eventually becoming one of the largest quick-service chains in the world. While individual stores once produced donuts on-site, modern Dunkin' systems rely heavily on centralized production facilities and commissaries that prepare donuts in large batches before they are delivered daily to outlets. This shift to centralized baking ensures consistency, efficiency, and food safety at a scale that would be difficult to achieve if every location produced donuts independently. The process begins with raw ingredients, the most essential of which is flour. Flour is typically sourced from regional mills that produce high gluten varieties suitable for yeast-raised donuts. Gluten strength is important because donuts require a dough that can expand and hold air pockets during proofing and frying, creating the light, fluffy interior consumers expect. The flour arrives at commissaries in bulk trucks and is stored in large silos equipped with pneumatic conveying systems that deliver the flour directly to mixing machines when needed. Alongside flour, sugar is a critical ingredient both for sweetness and for feeding the yeast in raised donuts. Sugar is also delivered in bulk and carefully weighed by automated systems. Other ingredients include dried milk solids, shortening or vegetable oils for richness, salt for balance, eggs or egg replacers, and specialized donut mixes that may contain dough conditioners to optimize texture and shelf life. Yeast is essential for the production of yeast-raised donuts, while chemical leaveners such as baking powder are used in cake donuts. Flavorings like vanilla and nutmeg are often incorporated for signature profiles. All of these raw materials are inspected on arrival to ensure they meet quality specifications, with testing for moisture, purity, and microbial safety. Mixing is the first major transformation step. Large horizontal mixers, sometimes called spiral arm mixers, combine flour, water, sugar, yeast, and fats into a homogeneous dough. The dough must be mixed to a specific level of gluten development, which gives it enough elasticity to expand without becoming tough. Mixing time and temperature are carefully controlled, since yeast activity begins as soon as the ingredients are hydrated. For yeast donuts, the dough emerges as a smooth, slightly tacky mass that is ready for fermentation. Cake donut batters, on the other hand, are much looser and resemble thick cake batter rather than bread dough. For yeast-raised donuts, the next stage is fermentation, also called proofing. Dough is placed into large troughs or hoppers and kept in temperature and humidity-controlled chambers. The yeast consumes sugars and produces carbon dioxide, which inflates the dough and develops flavor. Proofing times can vary, but typically the dough rests for 30 to 60 minutes until it has doubled in size. Automated proofing systems monitor conditions precisely to ensure consistent results across batches. Cake donut batters, being chemically leavened, bypass long fermentation and proceed directly to depositing. Shaping the donuts is accomplished by specialized forming equipment. For yeast-raised varieties, dough is sheeted and cut using rotary cutters or stamping machines that punch out rings, bars, or other shapes. Scrap dough is collected and recycled into subsequent batches. For cake donuts, depositor machines extrude batter directly into hot frying oil through ring-shaped nozzles, instantly forming the characteristic donut shape. Jelly-filled or cream-filled donuts are typically cut as solid discs without holes. Modern forming machines can produce thousands of donuts per hour, each with an identical size and weight to maintain uniform cooking times. Frying is one of the most critical steps in donut production. Industrial fryers, often designed as long troughs filled with hot vegetable oil, cook the donuts as they move along conveyors. The oil is maintained at a precise temperature, usually between 180 and 190 degrees Celsius, to ensure that the exterior forms a golden, crisp crust, while the interior remains tender and fluffy. Donuts float on the surface of the oil, and automatic turning devices flip them halfway through to ensure even cooking on both sides. The time in the fryer is short, often less than 2 minutes, but during that time, the transformation is dramatic. The dough or batter puffs up, moisture rapidly evaporates, and a rich golden brown surface develops. Oil quality is carefully monitored, with filters removing crumbs and sediment to prevent off flavors. Oil is replaced regularly to maintain consistency. Once fried, donuts are conveyed onto cooling racks or conveyors where excess oil drains and the surface temperature drops. At this stage, they are ready to finish. The finishing stage is where Dunkin' Donuts showcases its wide variety of flavors and styles. Plain donuts may be dusted with powdered sugar or cinnamon sugar in tumbling drums that evenly coat the surface. Glazed donuts are passed through glazing waterfalls where a thin curtain of sugar glaze envelops the donut, creating a shiny, sweet coating once set. Frosted donuts are topped with chocolate, vanilla, or strawberry icing applied either by enrobing machines or by automated depositors that spread a uniform layer across the surface. Decorations such as sprinkles are applied immediately after frosting, while the surface is still tacky. Automated sprinkling machines drop measured amounts of colored sugar or chocolate sprinkles, ensuring even coverage without waste. Filled donuts, such as jelly or Boston cream, are injected with fillings using pneumatic filling machines. These machines use nozzles to pierce the side of the donut and deposit a measured dose of fruit preserve, custard, or cream into the center. Each filled donut is checked by weight to confirm the correct amount of filling. Quality control is constant throughout finishing. Workers and automated vision systems check for uniform size, even frying color, complete glaze coverage, and accurate filling. Donuts that are misshapen or improperly coated are discarded or sent to waste recovery. The finished donuts are then arranged on trays or packaged into transport containers for delivery to retail stores. Centralized production facilities typically operate overnight, producing donuts in large batches that are delivered to Dunkin' outlets each morning. Trucks equipped with racks or crates transport the products under controlled conditions to maintain freshness. At the store level, donuts are displayed in cases for customers, often alongside freshly brewed coffee, which has become as important to Dunkin's identity as its donuts. Behind the scenes, Dunkin's donut production is an example of large-scale industrial baking. Every step, from bulk ingredient handling to automated frying and glazing has been engineered for efficiency, hygiene, and consistency. Factories operate under strict food safety programs, including HACCP protocols, allergen control, and sanitation schedules. Workers wear protective clothing and follow hygiene rules to prevent contamination. Equipment is designed for easy cleaning, with stainless steel surfaces, automated cleaning-in-place systems, and oil filtration loops. The automation does not diminish the artistry, however. Dunkin offers seasonal and specialty donuts that require customized decoration or limited time flavors. These may involve hand-finishing steps in commissaries or store-level icing and topping. The variety keeps the brand fresh and appealing, while the core processes ensure the signature taste and texture remain constant. From a sensory standpoint, Dunkin' Donuts' success comes from its ability to balance lightness and indulgence. The yeast-raised donuts deliver a pillowy interior with a slightly chewy crust, while cake donuts provide a denser, more flavorful bite. The frying process gives both styles a characteristic richness, while glazes and fillings add layers of sweetness and texture. All of these qualities are engineered into the production system through careful control of ingredients, dough rheology, frying times, and finishing techniques. Distribution and storage also play an important role. Donuts are highly perishable, best consumed within hours of frying. Dunkin's logistics are designed to ensure freshness, with daily deliveries and rapid turnover at stores. Unsold donuts are typically discarded at the end of the day rather than carried over, reinforcing the brand's emphasis on freshness. The McDonald's breakfast story begins in the early 1970s when franchise owner Herb Peterson created the Egg McMuffin, a sandwich designed to resemble Eggs Benedict but adapted for fast food service. It featured a freshly cracked egg cooked in a ring, a slice of Canadian bacon, American cheese, and a toasted English muffin. This innovation sparked the growth of McDonald's breakfast menu, which expanded to include biscuits, bagels, pancakes, hash browns, and sausage sandwiches. Today, breakfast accounts for a large share of McDonald's daily sales, and its production relies on both centralized food factories and in-store assembly. Take the English muffin, for example. McDonald's does not bake these in-house. Instead, large commercial bakeries supply standardized English muffins to distribution centers. These bakeries use industrial mixers, proofers, and tunnel ovens to produce muffins with uniform size, crumb structure, and toasting properties. Once baked, muffins are cooled, packaged, and frozen or refrigerated for transport. At the restaurant, muffins are stored in freezers until needed, then thawed and toasted in high-speed toasters that deliver consistent browning in under a minute. Canadian bacon, or back bacon, is prepared in large meat processing facilities. Pork loins are trimmed, cured with brine solutions containing salt, sugar, and preservatives, and then cooked or smoked in continuous ovens. After cooking, the bacon is chilled, sliced into uniform rounds, and vacuum sealed into large packs destined for McDonald's kitchens. Restaurants keep them refrigerated and quickly reheat the slices on flat-top griddles as orders come in. The cheese slice used in the Egg McMuffin is American processed cheese, manufactured in large dairy plants. This cheese is formulated for excellent meltability and stable shelf life. It is produced by blending natural cheese with milk, emulsifiers and stabilizers, then heating and homogenizing the mixture before casting it into blocks and slicing it into individually wrapped squares. The cheese arrives at McDonald's locations ready to be unwrapped and placed onto hot muffins or eggs, where the heat melts it smoothly. Eggs are another key component, and they are handled in two distinct ways. For sandwiches like the Egg McMuffin, McDonald's uses whole shell eggs. Restaurants crack each egg into a circular ring mold on a griddle, ensuring a perfectly round shape that fits the muffin. Steam is added by covering the egg with a lid, which cooks it gently and evenly. For scrambled eggs and folded egg patties, however, the supply chain relies on liquid eggs processed in large egg-breaking plants. Eggs are washed, cracked, and separated by machine. The yolks and whites are blended, pasteurized to destroy pathogens, and packaged into cartons or pouches. At McDonald's, these liquid eggs are poured onto griddles or cooked in ovens to create fluffy scrambled eggs or folded omelette-style patties that can be assembled into breakfast sandwiches. Sausage patties are manufactured in industrial meat plants. Ground pork, seasoned with salt, pepper, and spices, is blended in massive mixers and portioned into uniform discs using automated forming machines. These patties are pre-cooked on high-capacity grills or in continuous ovens to ensure food safety and consistent doneness. Once cooked, they are quick frozen to preserve flavor and shipped in bulk to restaurants. Staff at McDonald's reheat them on flat-top griddles, where they develop additional browning and flavor before being assembled into sandwiches like the Sausage McMuffin. Hash browns are another hallmark of McDonald's breakfast, and their production is a feat of food engineering. In processing plants, fresh potatoes are washed, peeled, and shredded into long strands. The shreds are blanched briefly in hot water to inactivate enzymes and remove excess starch, which helps achieve the golden, crispy texture consumers expect. The blanched shreds are mixed with small amounts of seasoning and binding agents, then formed into oval patties using hydraulic presses. These patties are par-fried in vegetable oil to set the structure and give them a light golden crust. After par-frying, they are frozen solid and packaged for shipment. In the restaurant, frozen hash browns are deep fried to order in fryers filled with vegetable oil until crisp and hot, ready to be served in paper sleeves. Hotcakes or pancakes are supplied in frozen form from large-scale bakeries. These bakeries prepare batter with flour, eggs, milk, sugar, and leavening agents in huge mixing tanks. The batter is deposited onto heated steel belts or griddles in automated production lines that cook the cakes on both sides until fluffy and golden. The pancakes are then quick frozen and stacked with sheets of paper between them to prevent sticking. At McDonald's, they are reheated in microwave or convection ovens, then served with butter and syrup. Biscuits, available in certain markets, are also produced centrally. Industrial bakeries mix dough enriched with shortening or butter, laminate it to create flaky layers, cut it into rounds, and bake them in massive tunnel ovens. Once baked, biscuits are frozen and shipped to restaurants where they are reheated in convection ovens. Bagels follow a similar centralized process, being boiled and baked before freezing and distribution. Alongside food items, beverages like orange juice and coffee play a crucial role in McDonald's breakfast. Coffee beans are sourced globally, roasted in bulk by suppliers, ground, and vacuum-packed to preserve freshness. In restaurants, ground coffee is brewed in calibrated machines designed to produce consistent strength and flavor. Orange juice is pasteurized and packaged by beverage manufacturers, arriving in ready-to-serve containers. Milk and creamers are supplied in portion packs for convenience. The assembly process in restaurants is engineered for speed and consistency. Each component, eggs, muffins, bacon, sausage, cheese, hash browns, and pancakes, has a designated station on the production line. Staff are trained to assemble sandwiches in seconds, following standardized build charts. For example, an Egg McMuffin requires toasting the muffin, cooking the egg in the ring, reheating the bacon, adding cheese, and stacking them in the correct order before wrapping in branded paper. Every step is designed to minimize variation, so a customer in Tokyo receives the same product as one in New York. Behind the counter, holding cabinets and warming drawers play an essential role. Cooked items like sausage patties, hash browns, and scrambled eggs are stored at safe holding temperatures for a limited time, allowing staff to assemble orders quickly during peak morning rushes. Strict time limits prevent items from going stale, ensuring freshness. Food safety is paramount throughout the process. Ingredients are prepared in centralized facilities under HACCP protocols, pasteurized where necessary, and frozen to inhibit microbial growth. In restaurants, staff monitor cooking times and temperatures with digital timers and thermometers. Fryer oil is filtered daily, and cooking surfaces are cleaned on schedule. Eggs cooked to order are held to safe cooking standards, while liquid eggs are pasteurized to eliminate risk. Distribution logistics tie everything together. McDonald's operates a just-in-time supply system, with trucks delivering frozen and chilled ingredients from regional distribution centers several times per week. Restaurants rely on walk-in freezers, refrigerators, and dry storage to keep inventories fresh but lean, reducing waste. This system ensures a steady flow of muffins, eggs, meat, and potatoes to thousands of outlets worldwide. From a sensory perspective, McDonald's breakfast is engineered to deliver comfort and consistency. The toasted muffin provides a chewy base, the egg adds richness, the cheese melts into a creamy layer, and the Canadian bacon contributes savory saltiness. The hash browns supply a crunchy contrast, while hot coffee or orange juice completes the meal. Each element has been refined over decades to ensure it satisfies the expectations of millions of customers daily. The story of Krispy Kreme begins in 1937 when Vernon Rudolph purchased a yeast-raised donut recipe from a New Orleans chef and opened the first store in Winston-Salem, North Carolina. The unique flavor and light texture of his donuts quickly became popular, and the company grew steadily, eventually becoming an international brand. While the recipe has been closely guarded, the processes used to make Krispy Kreme donuts have been adapted for modern production, blending traditional dough-making methods with industrial automation. The process starts with the preparation of the dough. Krispy Kreme relies on specialized donut mixes supplied by large-scale flour milling and blending facilities. These mixes contain enriched wheat flour, sugar, milk powder, leavening agents, dough conditioners, and trace flavoring components that give the donuts their unique taste. The mixes arrive at Krispy Kreme shops in sealed bags or bulk silos. In each shop's back of house, industrial mixers combine the dry mix with water, yeast, and additional shortening to form the base dough. Yeast is critical here, as Krispy Kreme donuts are yeast-raised, which gives them their fluffy, airy structure compared to denser cake-style donuts. The dough is mixed until smooth and elastic, a process that develops the gluten framework necessary for trapping the carbon dioxide produced by yeast. Once mixed, the dough is transferred to proofing cabinets, which are temperature and humidity controlled chambers where the yeast ferments and produces gas. During proofing, the dough doubles in size, becoming light and airy. The careful regulation of proofing conditions ensures that every batch of dough has the same volume, texture, and flavor profile. After the initial fermentation, the dough is rolled out and mechanically cut into rings using rotary cutters. Krispy Kreme's machinery is designed to stamp out perfectly uniform rings at high speed. The distinctive donut holes, cut out from the center, are also fried and sold as mini treats. Dough scraps are collected, remixed, and fed back into the system, ensuring minimal waste. The cut rings are placed onto conveyor trays lined with parchment or mesh that prevents sticking and allows for smooth movement. Next comes the final proofing stage, where the cut donuts rest in specialized proofing conveyors, often called proofer cabinets. Here, gentle warmth and humidity allow the donuts to rise a second time, reaching their ideal volume before frying. This stage typically takes 30 to 45 minutes, and during this time, the donuts become visibly puffy and delicate, ready to be cooked. Frying is the most visually iconic part of Krispy Kreme production. The risen donuts are gently dropped into a long, shallow trough of hot vegetable oil held at a precise temperature, usually around 180 to 190 degrees Celsius. They float on the surface, and a mechanical arm flips them halfway through cooking to ensure even browning on both sides. The sight of rows of donuts flipping in perfect unison has become a hallmark of Krispy Kreme stores. Frying typically takes less than 2 minutes, during which the donuts puff further and develop a golden brown crust while retaining their pillowy interior. Once fried, the donuts are lifted from the oil and placed on a conveyor belt that carries them through the glazing station. This is the most famous stage of the Krispy Kreme process. A curtain of warm, liquid sugar glaze pours continuously over the donuts as they pass beneath, coating them evenly. The glaze is made from powdered sugar mixed with water, corn syrup, and stabilizers, kept warm to maintain a fluid consistency. Excess glaze drips through a mesh and is collected, filtered, and reused in a closed-loop system to minimize waste. The result is the glossy, translucent coating that cracks lightly when bitten into and melts instantly on the tongue. For donuts that require additional toppings, the glazed donuts may pass through secondary finishing stations. Chocolate or strawberry icing can be applied by enrobing or depositing systems. Some donuts are sprinkled with sugar, candy pieces, or cookie crumbs. Filled varieties, such as custard or jam-filled donuts, are injected with fillings using pneumatic nozzles that pierce the side of the donut and dispense a measured amount inside. Topping and filling stations can be partially automated or done by hand, depending on the complexity of the product. Quality control is essential at every stage. Workers and automated systems check that donuts are uniform in size, color, and coating. Any misshapen or undercooked donuts are removed from the line. The production process is designed to minimize defects, but Krispy Kreme emphasizes visual appeal as much as taste, knowing that customers often watch the production in store. What makes Krispy Kreme unique compared to many donut brands is that much of the production happens visibly in front of customers. Many shops have large glass windows where guests can watch the donuts moving along conveyors from proofing to frying to glazing. This transparency is part of the experience, reinforcing the perception of freshness and craftsmanship, even though highly automated machinery drives much of the process. Behind the scenes, the supply chain ensures that every Krispy Kreme location has the raw materials it needs. Central factories prepare the donut mixes, glazes, and fillings in standardized batches. These are shipped to individual stores on a just-in-time schedule to maintain freshness and reduce storage needs. Temperature-controlled logistics keep ingredients safe, while strict food safety systems oversee every step. At the store level, staff manage the machinery, monitor proofing and frying, and handle finishing. They also prepare seasonal and specialty donuts that may require extra decoration or unique toppings. For example, during holidays, Krispy Kreme often releases themed donuts with colored icings, sprinkles, or hand-piped decorations. These require skilled workers to apply finishing touches beyond what automated systems can handle. Hashing out the engineering, the donut line is an impressive example of bakery automation. It integrates mixers, proofers, conveyors, fryers, and glazing waterfalls into a continuous system that can produce thousands of donuts per hour. Temperature, timing, and humidity are all electronically controlled, ensuring consistency regardless of location. The system is also designed for food safety, with stainless steel equipment, clean-in-place systems for sanitation, and oil filtration units that remove debris and extend fryer oil life. The sensory profile of Krispy Kreme's original glazed is central to its identity. The donut is designed to be eaten warm when the glaze is still slightly tacky and the dough nearly melts in the mouth. The formula balances sweetness, fat, and yeast flavors to create a product that feels indulgent yet light. Achieving this balance requires careful control of fermentation, frying time, and glaze formulation. Distribution also plays an important role. Not all Krispy Kreme donuts are sold in flagship stores with production lines. Many are delivered to convenience stores, supermarkets, and smaller outlets. In these cases, donuts are produced in larger commissary bakeries and shipped daily. Specialized packaging maintains freshness during transport, though these donuts may lack the immediate appeal of those sold warm under the hot light. Marketing and presentation amplify the impact of the production process. The sight of fresh donuts moving under the glaze curtain has become iconic advertising in itself, shared widely on social media and forming part of Krispy Kreme's brand identity. Customers are drawn not just to the product, but to the theater of its creation. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, this water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, The water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform, sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company, but it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, the next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, The bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, a protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process. The industrial processing of honey begins not within the walls of the factory, but at the apiaries, where honeybees forage, collect nectar, and begin the complex enzymatic process of transforming floral sugars into the thick, golden liquid we know as honey. Factory-scale honey production starts with the careful coordination between contracted beekeepers and processing plants, which work together to supply bulk honey at a scale large enough to support mass distribution. The first step in the factory process involves the reception and inspection of raw honey as it arrives from the beekeepers' extraction sites. Raw honey is typically delivered in large food-grade steel drums or plastic totes, each capable of holding hundreds of pounds of honey. These containers arrive sealed, labeled with origin data, floral source if known, and batch tracking codes. Upon arrival at the honey processing facility, each container is unloaded onto the receiving dock, where a team of technicians begins the initial quality assurance process. This is far more than a visual check. Industrial honey processors must guarantee that the incoming product is pure, unadulterated, and meets strict legal and food safety standards. The drums are first sampled using a specialized honey sampling spear, a long stainless steel tube designed to pierce through the viscous mass and extract a vertical core from top to bottom. This is essential because honey can stratify, with moisture content, color, and crystallization levels varying from top to bottom. The extracted sample is then homogenized and sent to the quality control laboratory. Here, a battery of tests is performed. Moisture content is measured using refractometers, which determine how much water is present in the honey. Legal standards require honey to contain no more than 20% moisture to prevent fermentation. Beyond moisture testing, analysts perform pollen analysis to verify floral sources and geographic origin, which is important for regulatory labeling and for upholding claims like clover honey or orange blossom honey. Additional tests, such as electrical conductivity, help differentiate between nectar and honeydew honeys, while HMF levels, or hydroxymethyl furfural, are checked to ensure the honey hasn't been exposed to excessive heat during prior storage or transit. High-performance liquid chromatography may also be used to detect the presence of added sugars, which would indicate adulteration and result in immediate rejection of the batch. Once a drum passes inspection and is approved for processing, it is moved to the uncrystallization station. Raw honey can crystallize over time, particularly when stored in cooler environments or when the floral source is rich in glucose. Crystallized or partially crystallized honey must be reliquefied before it can be filtered or blended. This is achieved by placing the drums in heated chambers or warm water baths, known as hot rooms, where they are gently warmed to temperatures around 95 to 110 degrees Fahrenheit. This temperature range is sufficient to melt crystals without degrading the honey's delicate aromatic and enzymatic properties. Large facilities often use drum heating tunnels that can accommodate dozens of drums at a time. These tunnels employ radiant heat panels and convection fans that maintain a steady, uniform temperature throughout the enclosure. Temperature probes are inserted into each drum to ensure that internal temperatures rise slowly and evenly, preventing localized overheating which could darken the honey or degrade its quality. This gentle warming process can take anywhere from 24 to 72 hours, depending on the degree of crystallization and the initial temperature of the honey when it arrived. Now it's time to go into the liquefaction and transfer stage. where the now softened honey is pumped out of the drums and into the factory's primary processing line. This step requires specialized food-grade pumps capable of handling thick, sticky materials without introducing air bubbles or damaging the honey's texture. Positive displacement pumps, such as rotary lobe or progressive cavity pumps, are commonly used for this purpose. These pumps are designed to move viscous fluids at a steady rate without causing foaming or aeration, which can negatively impact downstream processing. As the honey is pumped from each drum, it passes through heated stainless steel pipelines that maintain a consistent temperature, usually around 110 to 120 degrees Fahrenheit, to keep the honey fluid during transit. The pipelines are insulated to minimize heat loss, and the entire system is cleaned between batches using CIP or clean-in-place systems, which circulate hot water and food-safe cleaning agents to maintain sanitary conditions. Valves and flow meters are used to control how much honey enters the next phase, which is usually a settling or holding tank. These tanks are large vertical silos equipped with gentle agitation paddles to keep the honey uniform without whipping air into it. At this stage, the honey is allowed to rest briefly, giving suspended particles like wax fragments, bee parts, or pollen clumps time to rise or settle. Some facilities incorporate slow-flow decanting chambers or skimming belts that remove surface foam and floating debris. The goal here is to prepare the honey for the critical filtration stage without exposing it to excessive agitation or temperature shifts, which could compromise quality. But up next is the filtration stage, one of the most technically controlled steps in factory honey processing. The challenge with filtering honey lies in removing impurities while preserving beneficial properties such as flavor, aroma, and trace pollen content. To accomplish this, processors use a series of progressively finer filters, starting with coarse metal mesh screens and moving to finer, micron-level filtration pads or cartridges. Initially, the honey flows through vibratory sieve filters or centrifugal strainers that remove large debris, including chunks of wax or bee remnants. These are often equipped with auto-cleaning screens that rotate or vibrate to prevent clogging. After coarse filtering, the honey enters a fine filtration system. Depth filters composed of cellulose or food-grade polypropylene are commonly used. These filters remove particles as small as 5 to 10 microns, including residual wax, dust, and crystallized sugar particles that could initiate recrystallization in the final product. To aid this process, the honey is maintained at a precise temperature of about 120 to 130 degrees Fahrenheit, warm enough to reduce viscosity and improve flow through filters, but not so hot as to destroy heat-sensitive enzymes or antioxidants. Inline temperature sensors and automated control panels ensure that every gallon of honey is processed under identical thermal conditions. Some advanced facilities even use vacuum-assisted filtration to further reduce the need for high temperatures, thereby preserving more of the honey's raw characteristics. Once filtration is complete, the honey is collected in large stainless steel blending tanks. These tanks are used to homogenize different batches of honey, standardize flavor profiles, and adjust final parameters such as color and clarity. Mixing paddles rotate at slow, controlled speeds to avoid aeration while ensuring a uniform blend. It's at this stage that some producers may add trace amounts of previously tested and approved batches to maintain flavor consistency across large volumes, especially if multiple floral sources are involved. Now it's time to explore the homogenization process in more detail, as this step plays a pivotal role in ensuring that every bottle or jar of honey pulled from the line is virtually identical in texture, color, and taste. Honey, being a natural product, can vary widely between batches due to differences in nectar sources, collection times, and even seasonal variations. To manage these inconsistencies, processors rely on computer-controlled blending protocols that match incoming honey against established reference standards. Before blending begins, technicians perform sensory and analytical testing on the batch, including color measurement using the Fund scale, which classifies honey from water white to dark amber. Flavor notes are assessed by trained sensory panels or electronic nose devices, while moisture and acidity levels are verified to determine blending ratios. If a batch is slightly darker than the standard product line, a portion of lighter honey is added to balance the color. If a batch is too viscous, a blend with a slightly higher moisture content is introduced to bring the final viscosity within specification. Mixing tanks used in this process are often jacketed with warm water or glycol to maintain the blending temperature at a steady 110 to 120 degrees Fahrenheit. Internal baffles guide the flow of honey, ensuring thorough integration without the formation of dead zones or stratification. The tanks are usually equipped with inline sensors that continuously monitor parameters like Brix, viscosity, and turbidity. The blending cycle may take several hours for large volumes, and throughout the process, automated samplers pull small amounts at regular intervals to verify that the blend remains within quality parameters. Once homogenization is complete, the honey is transferred to the final holding tanks that feed directly into the packaging lines. These tanks are placed on load cells that precisely measure the volume of honey dispensed into each container. From this point forward, the product must move through sealed, temperature-controlled systems to ensure no contamination occurs before bottling. And that leads directly into the highly synchronized packaging phase. As the homogenized honey flows from the final holding tanks into the packaging system, the entire process becomes a high-speed, tightly orchestrated sequence of mechanical precision and hygiene control. This stage is where the product begins to take on its final consumer-facing form, whether it's packaged in squeeze bottles, glass jars, tubs, or bulk containers. The packaging line starts with the selection and preparation of containers, which are fed into the system from large hopper units or depalletizers, depending on the container type. Plastic bottles often arrive pre-formed and stacked in bulk, while glass jars may come in pallets wrapped in protective plastic film. Regardless of material, every container goes through a rigorous cleaning phase before it is allowed anywhere near the honey. The first step in container preparation is an air rinse or ionized air cleaning process. Each container is inverted and passed through a chamber where blasts of filtered, pressurized air are directed inside. Ionized air is used specifically to neutralize any static charges that might cause dust or particles to cling to the sides of the container. In glass packaging lines, this process may be supplemented with a vacuum extractor that removes dislodged particles immediately after the air rinse. Some facilities also opt for a UV light exposure chamber that the containers pass through as an added antimicrobial safeguard. All of these steps are executed on automated conveyor systems, synchronized to keep pace with the fill line. Now it's time to go into the filling stage, which must be executed with extreme accuracy to ensure every package contains the correct weight or volume of honey. Honey's thick, slow-moving consistency makes it a challenging product to fill efficiently at scale. To meet this challenge, factories use volumetric piston fillers or gear pump filling machines, both of which are well suited for handling viscous, sticky products. These machines are equipped with heated nozzles and jacketed tubing to maintain the honey at an optimal temperature, typically around 110 degrees Fahrenheit, so it flows smoothly without foaming or dribbling. Each filling station is designed with multiple nozzles, often ranging from 4 to 16, depending on the line's speed and scale. The nozzles are programmed to descend into the containers during filling and retract as the level rises, a method known as bottom-up filling. This minimizes splashing and helps prevent the introduction of air bubbles, which can interfere with the product's shelf stability and aesthetic appearance. Inline check weighers are stationed just downstream of the filling heads, automatically rejecting any underfilled or overfilled containers from the line. Any deviation outside a narrow tolerance window triggers an immediate alert and mechanical removal. Immediately after filling, the containers are transferred to the capping and sealing station. For plastic bottles, this often involves a torque-controlled capper that applies precise rotational force to ensure a tight but not damaging seal. Flip-top caps, disc-top caps, or screw caps are automatically sorted and fed into place using vibratory feeders and cap chutes.